names of the participants as well. So we'll start in a while. Just yeah. So we are here, almost the last but one talk of the workshop, and I will request Professor Boyle to start because I mean, like we are going behind the schedule. So, Professor, can you please start?
Okay, thank you. Yes, so I'll share my screen here. Okay, you can all see that?
Yeah, it is visible.
Okay. Oops, this is not working. Okay, so great. So let me just briefly recap to set the stage for this lecture where things stand at the moment. So I won't write out the table in full, but if you want, the summary of the first lecture was our beloved table here with its with so many entries. So it was this 3 by, so there was SU3 times SU2. That's too ugly. Sorry. I wanted to do it quickly, but that's just a mess. Okay, so, you know, the summary of the first lecture was that we have this table with 6 rows of fermions and one scalar field. I won't fill in the numbers, but you know, the idea is that once you've written down this table, which says both what the standard, what the symmetries of the standard model are, and also how the matter fields transform under those symmetries, what representations they live in, then you have all the information you need to write down the standard model of particle physics, the Lagrangian. So we're left with some questions. At that stage, we're left with some questions. So, why is the standard model gauge group G standard model? Why is that SU3 times SU2 times U1? Why is the representation under which the fermions transform Rho standard model? Why is it this bizarre representation we wrote down last time? F plus F star, which if we expand it out really is a reducible vector space with 12 different components, each of which has kind of, rather bizarre properties. This table is full of all sorts of weird numbers like 1/6 and 2/3, etc. Why are there 3 generations of fermions? So if we really, this is the representation for a single generation of fermions. The actual representation for the total set of fermions in the standard model is 3 copies of this. So it's really F plus F star plus F star plus F plus F star. This whole pattern is repeated 3 times. So why is that? And then finally, when we write down the standard model Lagrangian, we find that we can write down about 20 different terms, or 20-something different terms, each of which is independently invariant, so each of which can have an independent real number appearing in front of it, real coefficient appearing in front of it. So there's 20-something undetermined parameters in the standard model. And it's natural to ask, can we explain any of those? Can we predict any of their values? Can we predict any relationships between them? Okay, so those are sort of some of the most pressing questions with the standard model, and that remain unanswered. But in terms of progress on these questions, well, in my opinion, the biggest insight was the one we discussed in the previous lecture, which was already made back in the 1970s, which was grand unification. And we summarize that by saying that, the standard model could be neatly embedded in the group SU5, which could in turn be neatly embedded in the group spin 10, which physicists usually call SO10. And when we do that, the representation of a single standard model generation gets neatly reinterpreted as lambda C5, the exterior algebra in 5 complex dimensions, and then in turn gets even more unified as the Dirac spinor of spin 10. And so, in other words, once we've gone to spin 10, it's basically saying that this complicated table up here, this 3x6 table with its 18 sort of random seeming entries, gets replaced by a simpler table which only has 1 row and 1 column. So down here, the table would look like, the analogous table would look like this. It would have 1 column, spin 10, and it would have 1 row, which is the single standard model fermion, and the entry would just be the Dirac spinor. Well, really the analogous, anyway, yeah. If I was really using the analogous notation to the above table, I would have written the 16 here, which is the Weyl spinor. And then that's the particle, and then the Dirac spinor is 16 plus 16 bar. That's the particle and antiparticle. But anyway, it becomes a 1x1 table, so that looks like a huge improvement. Again, it's hard to believe that's just a coincidence that this starting table can be rewritten as so neatly as a 1x1 table. But we're still left down here with questions. This is, even if this is an improvement, we could still ask why spin 10? What's that about? Why the Dirac spinor representation? Spin 10 has an infinite number of representations to choose from. Why the Dirac spinor? It does seem rather natural, but and then again, we've made no progress. One thing grand unification does not answer is why 3 generations. We make no progress on that. And then now we're still at this question of why do the parameters have the values that they do? This SO10 theory will have fewer parameters than the standard model does. So we've made some improvement on that question. The SO10 theory will have fewer parameters in the UV theory, but then at low energies we should expect some predicted relationships among the standard model parameters at low energies, and it's a bit of a mixed bag whether that works or not. I'll explain that a little bit more. But so SU5 makes some predicted relationships between the parameters in the standard model in this way, and as a consequence, although those predictions seem like they're on the right track, they're roughly in the right ballpark. They're not actually right, and so SU5 without supersymmetry is ruled out for that reason. SO10 or spin 10 grand unification makes less specific predictions, and so the fact that it hasn't been ruled out is not good evidence that it's doing better in that regard. So spin 10, unfortunately, has not really yet so far. In principle, although in principle it could give us predicted values, the current observations don't actually give any non-trivial confirmation for the predicted parameter values in the standard model from SO10. As far as SO10 is concerned, the parameters in the standard model might as well still be independent. So although in principle you could expect some progress on this topic, also in practice there hasn't been. Okay. Okay, great. So now what I wanted to talk about now is that there has been a second, in my opinion, important insight, which was much more recent and is much less well known, and it was really initiated by, I think there have been a number of a handful of people, including myself, who over the years have toyed with the idea that the exceptional Jordan algebra, which I'll explain what it is, might be related to the standard model and might give some hopefully deeper explanation for where the standard model comes from and where to go next. But you know, I was never really able to make it work. I was never able to see what there were some numerological connections, but I was never able to make a detailed connection work. And apparently this guy Todorov has been playing with the same thing, and he did find a very interesting connection back in 2018 when he was, I should add, when he was 86 years old at the time. So it's a sort of inspiring story. I hope I'm writing papers that good when I'm 86 years old. So anyway, he found an interesting connection, which I want to tell you about between the standard model and the exceptional Jordan algebra. And then on top of that, I want to explain to you a follow-up paper, which I wrote this summer, about how if you complexify the exceptional Jordan algebra. See, with Todorov's story, it doesn't yet properly include the fermions in the standard model. And so it doesn't properly connect to our previous hint about SO10. And basically, I explained in a paper this summer how if you complexify the exceptional Jordan algebra, you
Is it Euclidean Jordan algebra?
Yes. Thank you. I'll explain what that means in a moment. Yeah, but yes, it is. Once you complexify it? No. Once you complexify it, it's not. Sorry, the classification that leads to the exceptional Jordan algebra, the standard way to do it is to classify the Euclidean Jordan algebras. And indeed, no, once you complexify, it's a Jordan algebra, but not a Euclidean Jordan algebra. That's a good point.
Okay.
But anyway, we'll get there. So that this object, which is related to a certain entry in something called a very interesting thing called the magic square, which I'll talk about. This is in addition to being an exceptional Euclidean Jordan algebra, it has another important role in the so-called magic square of exceptional Lie algebras, and so does this guy. This guy is the so anyway. I'm sorry. Well, I'm getting ahead of myself. I want to explain how when you work. How maybe it seems like this is the more correct object that relates to the standard model, and in a sense, connects what Todorov figured out to the earlier SO10 insight that we discussed in the previous lecture. Okay. Okay, great. So let me see. By way of, do I want to say anything else by way of introduction? No. So I want to introduce you to what the exceptional Jordan algebra is. And to do that, I should start by introducing or reminding you about the normed division algebras. R, C, H, and O. Okay, so these are the real numbers. These are basically the four. You know, you're all familiar, of course, with the real numbers and the complex numbers. The complex numbers are obtained by sort of doubling the real numbers. They live in a space of in a two-dimensional real plane. And you could ask, you know, how many other nice number systems are there like that, where I can add and subtract and multiply and divide, and the numbers have a natural notion of size, so that when I take the product of two numbers, the new number is the product of the previous two numbers' sizes. And there's a famous theorem that there's only four number systems like that: the real numbers, the complex numbers. We can double the complex numbers again to get the Quaternions, and then we can double one last time to get the Octonions, and then that's where the game ends. And so, of course, you all know what the real numbers are. The complex numbers you also are familiar with, of course, but just to sort of introduce the later ones, let me just describe them this way. So, you know, a complex number is a number of the form A0 plus A1I, where A0 and A1 are real coefficients, and I is this number that's defined to square to minus 1. Okay, so then the Quaternions are numbers of the form Q equals, the Quaternions, by the way, are called H, both because Q was taken, Q is mathematicians usually use for the rational numbers, but also H is after Hamilton, who discovered them. Okay, so they're numbers of the form A0 plus A1I plus A2J plus A3K. So now there's three imaginaries, I, J, and K. They all square to minus 1. And then when you multiply two different imaginary numbers together, like I times J, the rule for how to multiply them is neatly summarized by a little picture here, where we imagine I, J, and K as being 3 points on a circle. And it's an oriented circle. And the idea is that if I multiply two numbers on the circle, then the answer is given by continuing around the circle. So I times J, I keep going around the circle, and I get to K. So I times J is equal to K, and there's a plus sign. It's equal to, oops. What did I just do? I times J is equal to K, and there's a plus sign because I moved in the same direction as the arrow on the circle. If instead, for example, I had taken K times J, so I started K here, I head towards J. I don't know what's going on with my, I'm not familiar enough with this program to know exactly what I'm doing wrong here, but I didn't mean to put that. So the point is that K if I multiply K times J, because I'm moving, the answer is minus I, because I moved in the opposite direction. I moved in the opposite direction from the arrow on the circle. Okay, so now finally, the octonions are obtained by going a step further here. You double things again. So now the complex numbers lived in a two-dimensional space. The quaternions live in a four-dimensional space. There's four real coefficients: A0, A1, A2, and A3. The octonions are numbers of the form A0 plus A1i plus A2j plus A3k plus A4l plus A5il plus A6jl plus A7 KL. Okay, so now there's 7 imaginaries, which all square to -1. So I squared equals J squared equals K squared equals L squared equals IL squared equals JL squared equals KL squared equals -1. And now, again, if we want to multiply two different imaginaries, the rule for multiplying two different imaginary octonions is given by a picture analogous to this one, but a little bit fancier. So let me give myself another page to draw it on. So a picture called the Fano Plane. Where the idea is that okay, so this is supposed to be a diagram with 7 points now. Okay, the 7 dots that I've drawn. And each of these dots corresponds to one of the imaginaries. We have I, J, K. L is in the middle. And then IL, JL, and KL are around the corners of the triangle. Okay, so there's 7 dots corresponding to the 7 imaginaries. There's also 7 lines corresponding to oops. There's also 7 lines corresponding to the any 3 dots lie on a line here. So the 7 lines are the 3 edges of the triangle, the 3 altitudes of the triangle, like this one, this one, and this one. And then we're going to count this circle as another line. And then each of these lines has 3 dots on it, and each of these 7 lines, and each of them is going to function just like the circle did in the previous quaternion diagram. So I'm going to imagine each of these 7 lines is wrapped up into a circle, and each of them is oriented just like the quaternion circle was. Okay. And so this diagram, if you take any 2 points on this diagram, you'll find there's a unique line that they lie on, and you can follow that line to determine what their product is. So for example, I times L. Oops, I think I oriented I oriented these lines incorrect. The altitudes, I gave the wrong orientation. So this diagram says that I times L is equal to IL, for example. I start with I and L, and I follow them up this line to get to IL. Or another example would be that K times IL, I would go this way and cycle back around here to get to JL, but with a minus sign. So K times IL is equal to minus JL. Okay. So anyway, that's what the octonions are. So, well, let me just add, so an important fact about the, that's kind of emerged over the 20th century is that, mathematicians love to classify things. They love to find interesting objects and then classify them. And again and again, a pattern appears in many different parts of mathematics, which is that you find some interesting set of objects like groups or Lie algebras or manifolds with special holonomy or Jordan algebras, like we'll see in a moment. And you classify them and you find that they fall into a few infinite families, which are sort of the normal cases. And those infinite families, those few infinite families correspond to the real numbers and the complex numbers and the quaternions. And then there's a finite set of special leftover cases, exceptional cases that don't fit into the normal families, the normal infinite families. And those finite set of exceptional cases end up corresponding to the Octonions, or being described by the Octonions. And so, okay, yeah. So we'll now see that. Yes.
Yeah. What will be L times IL, J or minus J?
Oh, say that again.
What will be the result of L times IL?
L times IL. Okay, L times IL. According to our diagram, because the arrow should be pointing this way. So L times IL will be going in the same direction as the arrow, and we'll follow that line to the third point on that line, which is the point I here. So L times IL will be I, plus I. Does that make sense?
Oh, okay. Okay. Yeah.
So if you take any pair of points that you want to multiply, those points always lie on a unique line, one of the 7 lines, and then there's a third point on that line, which is the product, which is their product. Okay. Okay, great. So now let's. So now I want to introduce the Jordan algebras, but let's start by just reminding you what an algebra is. Period. So an algebra is, what a mathematician means by an algebra is a vector space where you can take the product of 2 vectors to get another vector. So it's a vector space that's equipped with a product where you can take the product of 2 vectors to get a third vector, and that product is bilinear in the 2 arguments. So it basically obeys the normal distributive law. So it's a vector space with a bilinear product. From V times V to V. The product of 2 vectors gives another vector. So for example, the Octonions are an example of an algebra. They're an 8-dimensional algebra over the real numbers, because I can take the product of, they form an 8-dimensional vector space, but then I can also take their product, as described by the Fano diagram. N by n matrices form another algebra. They form a vector space, of course, because the any linear combination of 2 n by n matrices is another n by n matrix. But I can also take the product of them, product of 2 matrices, taken with the ordinary matrix product to get a third matrix. Okay, and so one important type of algebra, which comes up, of course, in physics, are Lie algebras. So these arise as the infinitesimal generators of the symmetries that appear in physics, and so these are algebras that where the product behaves as if it was where the product is the so-called Lie bracket, or the commutator. So that's the product in the algebra is antisymmetric. And then it's also, you know, if you think about A and B as being like matrices, and this product is the what you would normally call the commutator of those matrices, then it's not associative. So it's not associative because in general the product of A with B, and then we take the product of that with C, is not in general equal to first taking the product of B with C and then taking the product with A. Okay, so it's not associative, but there's a replacement for the associativity condition, which is the so-called Jacobi condition. So instead, they satisfy this property that commutator of A and B with C, and then plus cyclic permutations of that. That does vanish. Okay, so that's what a Lie algebra is, and then the compact semi-simple Lie algebras were famously classified by Lie and Cartan and Killing, I guess, and famously they come in. Usually one expresses the classification in Dinkin diagrams, in which case you say there's 4 infinite families: AN, BN, CN, and DN. And then there's a handful of exceptional cases. There's 5 exceptional Lie algebras called G2, F4, E6, E7, and E8. Now, in terms of, you know, actually there's a nice way to express the normal cases, as I mentioned before, in terms of the norm division algebras. These are the Lie algebras of there's really 3 infinite families when you express it that way. There's the 3 infinite families being the antisymmetric n by n matrices with entries in the reals. Then there's the antisymmetric n by n matrices with complex entries. I should say antisymmetric. I should have said anti-Hermitian. So then, and then in other words, A dagger is equal to minus A are the elements in here, and then the anti-Hermitian elements, anti-Hermitian n by n matrices with entries in the complex numbers. So these are this is the Lie algebra SON. When you put complex numbers in, that's SUN, and when you put quaternions in, that's SPN, the symplectic Lie algebra. Okay, and then you might say, what about these exceptional cases? Do they, you know, you might suspect based on that previous pattern that these guys have something to do with the Octonions. And they do, but exactly what the relationship is a little bit subtle to state, and it's described by this thing that was discovered in the 50s and 60s called the magic square, which I'll get to explain a little bit later. Okay, but so much for Lie algebras. Let's talk about Jordan algebras now. Okay. So, you know, in short, the idea was that in the early days of quantum mechanics, Jordan, one of the pioneers of quantum mechanics, you know, when you learn about quantum mechanics today, most people, the way they learn about it, the way I learned about it, is that, you know, you work with matrices that act on Hilbert space. And those matrices form an ordinary matrix algebra. You know, the product between 2 matrices is the matrix product. So most of those matrices are not Hermitian, but for some reason, the only ones you can observe are the Hermitian ones. So the observables are the Hermitian matrices, but when you're actually doing quantum mechanical calculations, you sort of work with an algebra where most of the elements in the algebra aren't observable. They're not Hermitian. So Jordan wanted a reformulation of quantum mechanics that was purely in terms of the observable objects, the Hermitian guys. But it couldn't that algebra of quantum observables can't be the normal matrix algebra, because if you take two Hermitian matrices, H1 and H2, and you take their ordinary matrix product, that's not Hermitian anymore. This thing, if you take its dagger, it's not equal to H1, H2. So they don't form a nice algebra. Hermitian matrices don't under the ordinary matrix product. And so he realized, instead what you should do is you should take their anti-commutator, which is H1, H2 plus H2, H1. So now if you take the anti-commutator of two Hermitian matrices, you do get another Hermitian matrix. So they do form a nice algebra with that product. And that's the template for what a Jordan algebra is. So I won't get into the details, but Jordan gave the, so that this product is no longer associative, just like in the Lie algebra case. If we first take the product of H1 with H2, and then take the product with H3, that's in general not equal to first taking the product of H2 with H3, and then taking the product with H1. But it instead satisfies a different condition, which is analogous to the Jacobi identity as a replacement for associativity. And anyway, Jordan, this is not the place to get into the details, but Jordan sort of characterized axiomatically what an algebra like this, what properties it should have in order for the basic structure of quantum mechanics to make sense. Where you need to have observables that well, anyway. So based on this template, he defined this notion of Jordan algebra, and then shortly thereafter, or Euclidean Jordan algebra, and shortly thereafter, these were classified by Jordan and. Yes.
I just want to ask one question.
Yes.
Means the way you have introduced anti-commutator, it is reminiscent of the this Boyle ordering, no? Of operators. Has it something to do with that? Boyle ordering operators?
That's a good question. I don't know, now that you mention it. Maybe so, but I don't know. That's a good question. I'd have to think about it. Biswajit, thank you. Okay, so Jordan and von Neumann and Wigner classified these, and the story is very analogous to the Lie algebra case. There's a handful of infinite families, and then there's a finite number of exceptional cases left over at the end. In this case, one of the infinite families are the so-called spin factor Jordan algebras, which I won't say what they're very simple, but I won't mention them here because they're not immediately relevant for this story. And then the other three infinite families are now the n by n real Hermitian matrices. So in this case, with real matrices, Hermitian is the same as symmetric. So n by n real matrices that are symmetric, and you give them the product is the anti-commutator, just like we said above. So that's one set. That's one infinite family of Jordan algebras. That's an algebra. In other words, it's an infinite family because n can take on any value, 1, 2, or 3, or 4, etc. Or you could take the n by n Hermitian matrices with complex entries in the matrix, or the n by n Hermitian matrices with quaternionic entries. And then again, so those are the infinite normal families. And then, as I said, there's a handful of exceptional cases left over, a finite number of exceptional cases that don't fit this classification. Well, actually, in this case, there's only one exceptional case left over that doesn't fit the classification, and that's the so-called exceptional Jordan algebra. So that's the algebra of 3 by 3 Hermitian matrices with entries that are octonions. So in other words, an element of this algebra is a 3 by 3 matrix that's Hermitian. So its diagonal elements are real numbers, alpha 1, alpha 2, and alpha 3. And its off-diagonal elements are octonions, 3 octonions, but it's Hermitian, so that there's only 3 independent octonions, because if you take the dagger, it's equal to itself. So here we have the octonion x1, but then here we have its dagger across the diagonal. And here we have the element x2, but here we have its dagger, its conjugate, I should say. And here we have x3 and x3 conjugate. Okay, and so it's matrix. This is the algebra of matrices like this, with the product again given by the anticommutator of these matrices. If you take the anticommutator of 2 different matrices like this, you'll see you get another matrix just like this. Okay, so that's what the exceptional Jordan algebra is. Good. So now, what did Todorov realize about this algebra? Well, so he realized that so if you take the automorphism group of this algebra, the set of linear transformations, the symmetry group of the algebra, the set of transformations of the algebra to itself that preserve its product and are invertible, those form one of the exceptional Lie groups I mentioned on the previous slide. It forms the exceptional group. So the automorphisms of H3O form the exceptional group F4. Okay, but and F4 doesn't seem like it has anything particular to do with the standard model. It's in particular, it doesn't show up as a gauge group in any grand unification schemes, for a reason I'll get back to later. But nevertheless, what Todorov noticed was that if you look at 2 maximal subgroups of this that have a very natural interpretation in the exceptional Jordan algebra, then their intersection is exactly the standard model gauge group. So what are those 2 subgroups? So first of all, let's look at the subgroup of transformations that, let's imagine we split up the algebra like this. Okay, so let's imagine, let's look at the transformations that preserve this splitting. So they carry this element into itself. It turns out they leave that element alone. They carry this 2 by 2 matrix into itself, and they leave the off diagonal columns to carry them into themselves also. So they mix up. In other words, they mix up these elements, but they leave this 2 by 2 block alone. They mix within that 2 by 2 block. So that subalgebra turns out to be spin 9. Now, a different subalgebra you can look at is, you can look at the subalgebra that takes each octonion, and so each octonion is some number of the form x0 plus x1i plus ... But so the first 2 numbers in the octonion are a complex number. So there's a natural embedding of the complex number. I mean, not the complex numbers are embedded in the octonions. Now, it's arbitrary how they're embedded. they could, we could have taken x0 plus x2j and called that a complex number. There's many different ways to split up the Octonions, so that there's many different ways of embedding the complex numbers in the Octonions. But if you pick one, you can pick any one you want, and now you look at the automorphisms of H3O that preserve that embedding of the complex numbers in the Octonions, then that gives a different subgroup here. That different subgroup is SU3 times SU3 mod Z3. And so let's call the first subgroup H1 and the second subgroup H2. The details of what those subgroups aren't so important, but the point is that what he finds is that H1 intersection H2. If I look at the symmetries of the exceptional Jordan algebra that do both, that preserve the 2 plus 1 splitting, and that also preserve the embedding of the complex numbers, that is exactly the group SU3 times SU2 times U1 mod Z6. So this is exactly the standard model gauge group. In fact, the Z6 is a part of the standard model gauge group that I hadn't mentioned yet, but that Z6 is so that this is more precisely what the standard model gauge group is. This is what you get from SO10 unification. That SO10, part of the success of it is that it doesn't just predict SU3 times SU2 times U1. It predicts that mod Z6, which then gives a very natural explanation for why all of the charges that you see in the last column of the standard model table are multiples of 1/6, why they're quantized. Okay, so that's his observation, and now that may not sound like much, but then John Baez noticed the paper and wrote a kind of nice blog article making an observation, giving a geometrical interpretation to that observation. So he said, oh, wait a minute. So, okay, let's have my algebra back here. So,
Latham, a couple of questions.
Yes.
The standard model, the Z6 you have quotiented it with, I just wonder, has it something to do with this some roots of unity kind of thing? Is that people sometimes talk about PSUN and then SUN quotiented with the nth root of unity, that kind of thing.
Yes, it is related to that. Yes. Yeah, that's basically right. Yes. What I'm trying to say. What else should I say about that? If you let's see. If we go back to because I still have the old slides here. Where's the right place to look? By the way, when I do this, you guys can see me flipping through my slides, right? Yes, you can, I think. Oh, I can't spot the right slide at the moment, but
okay, maybe we can discuss it later after you
okay,
talk.
shoot. Yeah, sorry. Okay, let's discuss it later. Yeah, sorry about that. But in short, yes, it is related.
Anyway, another question that I just want to ask. You have, I'm not very much familiar with this Octonion thing. I just wonder for the Quaternion thing, you see, when you write some Q naught plus some I times some Q1 plus J times Q2 plus K times Q3 kind of thing, and I squared, J squared, there something like three sets of, like you have imaginary number which squares to -1, and then some additional condition ij product is k and cyclic and things like that.
Yeah.
So, but we can give some 2 by 2 matrix representation of these things in terms of Pauli matrices.
Right.
So
Right.
I wonder whether for Octonion also some matrix representation is possible or not.
No, it's not possible in the Octonion case because they're not associative.
Okay.
Yeah. The people. There's a so-called Zorn representation that tries to do something analogous for Octonions, where they represent them as matrices, and it can be kind of helpful for remembering how the product works, but it doesn't use the normal matrix product. Okay, so let's see. So yeah, let's say Baez's interpretation here. So Baez points out, okay, first of all, this exceptional Jordan algebra, in a way that I won't have a chance to explain here, but every all of these HNR, HNC, each of these Hermitian Jordan algebras has a corresponding dual interpretation as a projective space. So Hn of R there's an exact correspondence between the algebra HNR and the projective space RP and the n-1 dimensional real projective space, which and it's not crucial to know what that is. I just want to get an idea across here. And then for CN for HNC, that Jordan algebra corresponds to the corresponding complex projective n-1 space, and for the Quaternions, it's the corresponding quaternionic projective space, and this exceptional Jordan algebra corresponds to the so-called octonionic projective plane, or the Mufang plane, which is a kind of special geometrical object that mathematicians have been interested in for a long time. And so this algebra has an element, has a natural interpretation in terms of this dual geometric space, the octonionic projective plane. And the automorphisms of the algebra in particular are nothing but the isometries of that projective plane. So Baez points out that now if you look at the two subgroups that Todorov considered, that he fixed, so the first thing he did was he fixed a subgroup that that split up the algebra like this, gave it this 2 + 1 split. But Baez points out that that has a geometric interpretation that corresponds to, see, this 2 by 2 algebra that he's fixing it's a 10-dimensional algebra, okay, because it has 2 real numbers on the diagonal and 8 more real numbers off diagonal. So it's a 10-dimensional vector. It's a 10-dimensional vector space, and then that vector space is equipped with a natural norm, natural quadratic norm, which is the natural quadratic form, I should say, which is the determinant of that 2 by 2 matrix. And if you look at that determinant, you'll see that it gives that vector space a quadratic form with signature 1, 9, basically 1 plus sign and 9 minus signs, because basically if you imagine writing this, the real element here is the upper real, yeah, sorry, if you imagine writing this 2 by 2 matrix, you could write it as x0 plus x9, and then x0 minus x9 is the bottom diagonal, and then the real numbers on the off diagonal, the Octonions are like x. I'll now write them as x1 plus x2i plus da 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 da, up to x8. You know, KL, and then the complex conjugate down here. So if you take the determinant of this thing, you'll see it's like x0 squared minus x1 squared minus x2 squared minus dot 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 minus x9 squared. So in other words, this is a 10-dimensional vector space equipped with this natural quadratic form. Well, that's nothing but Minkowski space. That's exactly 10-dimensional Minkowski space. The space that famously comes up in various spaces, various speculations about physics beyond the standard model for various reasons, and in particular, it's famously the space that string theory wants to live in. Okay, so that's one thing. Now, when we intersect that group with the second, with Todorov's second group, so in other words, when you fix, when you not only look at the subgroup that fixes this 2 by 2 block, but you also look at you also impose the condition that the automorphism should preserve the embedding of the complex numbers in the Octonions. Well, then you're looking at 2 by 2 matrices of this form, x0 plus x3. You know, that turns out to fit, that ends up fixing the 2 by 2 complex matrix, complex analog of this matrix, the complex part of this matrix. So it ends up fixing you know, the complex part of the previous matrix, and this is nothing but 4D by the same argument as above. This is nothing but a copy of 4D Minkowski space when regarded as a vector space with a quadratic form. And so Baez just has this kind of interpretation that you start with the geometric space. Another way to say what Todorov is doing is that he's starting with a geometric space, and then he's the octonionic projective plane, and then he's first fixing. He's asking for the symmetries that fix a certain geometric subspace, which has a geometric interpretation as a copy of 10-dimensional Minkowski space, and then he further restricts to the symmetries which also fix a copy of 4D Minkowski space, which is embedded in this 10D Minkowski space. So we have a 4D Minkowski space embedded in 10D Minkowski space, which is in turn embedded in the octonionic projective plane. And the statement is that the subgroup of the automorphism group of the algebra that preserves that chain of embeddings is the standard model gauge group. So when you say it that way, it seems quite striking. So it's not exactly clear what's going on. I mean, I don't, you know, this is certainly not like a full physical theory, but it's just a kind of striking way to state what the sort of algebraic fact that Todorov found. So that got me thinking about this, and it got me thinking even more about it. And so just to say, the one additional thing which I found thinking about this is that okay, so again we have our 3 by 3 algebra, and we've kind of split it into a 2 by 2 block and a 1 down here. And so far the discussion has been, you know, about the, let's say, the block diagonal parts of this matrix. But you could ask, you know, well, okay, so far that the discussion has been all about the symmetries of the standard model, but where do the matter fit into this story? If this is really related somehow to the standard model, you know, where are the fermions? And a natural guess would be, oh, well, here in the off-diagonal components, which we haven't looked at here yet, you know, we have 2 octonions, so that's a 16-dimensional off-diagonal vector. You know, could it be that in some sense these 16 numbers, which get mixed up by the same symmetries, could it be that those are nothing but the fermions in the standard model, and that they're getting mixed up exactly as the representations in the standard model get mixed up? Well, no. The answer is no. In the real exceptional Jordan algebra, the answer is it just doesn't work. You know, once you've found your standard model subgroup here, then you have no freedom. It mixes up these guys in a certain way, and it is what it is, and it's not the way the standard model works. But the thing which I noticed is that if you go to the complexified Jordan algebra and do the exactly analogous thing that Todorov did, then it does work. Okay, so let me just explain what I mean by that. So I'm going to now look at the complexification of the exceptional Jordan algebra. Okay, so I'm going to go from H3 of O to its complexification. Okay, so this was some 27-dimensional real algebra, and so now this is some 27-dimensional complex algebra. This is 27-dimensional real. This one down here is 27-dimensional complex. Okay, now what I want to do is consider the symmetries of this algebra in the sense motivated by the magic square, which I haven't had a chance to describe what the magic square is. But the magic square is an idea. Okay, let me briefly say what it is here. Well, just for I'll say in a moment more what it is. But the idea is that mathematicians, in particular Tits and Freudenthal, were wondering about how to relate the exceptional Lie algebras to the Octonions, and they noticed that that the first two, G2, was nothing but the automorphisms of the Octonions themselves, the symmetries of the Octonions themselves, and F4 was nothing but the automorphisms of the exceptional Jordan algebra. And what they, roughly speaking, what the magic square is the idea that the remaining exceptional Lie algebras, E6, E7, and E8, are related to the complexified, quaternified, and octonionified exceptional Jordan algebra. Okay, I emphasize that is roughly speaking the idea, and I have to explain more correctly what the idea is. But so there's some process here where if we just take the real octonion, if we just take the real exceptional Jordan algebra, we get F4. But if, in some sense, if we combine the complex numbers with the octonionic exceptional Jordan algebra, we get E6. And then if we take the quaternionified version, we get E7, and the octonionified version, we get E8. But so in that story, the analogous thing we look for here, the symmetries of this complexified algebra, are the linear transformations of the algebra to itself, that preserve both the natural inner product. There's a natural inner product on this algebra, and also the determinant of the algebra. So if you did those things up here, you'd get F4. Down here, instead, you get E6. Okay, so the full symmetry group in that sense down here is now E6 instead of E4. And now, remember we had so up here we had F4 as the full symmetry group, and then we had these two subgroups. The subgroup that preserved the 2 to 1, the 2 times 1 splitting up here was spin 9. Whoops, what did I do? Was spin 9. Down here, the analogous subgroup that preserves the splitting is spin 10, which sounds nicely familiar from grand unification. And then the subgroup that up here that preserved the splitting, I'm making a mess here. Let me make myself a little bit more room. Up here, on the top, the subgroup that preserved the embedding of C in O, the embedding of C in O, complex numbers in the Octonions. In this case, it was SU3 times SU3 mod Z3. Down here, when we do the same thing, we find that it's we fix the embedding of the complex numbers in the Octonions. We get SU3 times SU3 times SU3 mod Z3. And now when we take the intersection of these two groups, up here, we got exactly the standard model. So if we took the symmetries that did both of these two things, as we said, we got the standard model. Up here, down below, if we now take the symmetries that exactly analogous to Todorov that preserve both of these structures, now the result is, let's see, I'll move down here. Now the result is not quite the standard model. Instead, it is the symmetry group of the so-called left-right symmetric version of the standard model. So this is the intersection of these two groups ends up being SU3 times SU2 times SU2 times U1. And so this is a famous group that has been studied by particle physicists that has been of interest to particle physicists for a long time. So they would call this SU2 left and this SU2 right. So the idea is that this SU2 left is the SU2 we all know and love from the standard model gauge group. And this SU2 right, it looks like the standard model, the fact that in the standard model, just like all the left-handed particles are grouped into doublets, like in addition, the up left is paired with the down left in certain ways, and the new left is paired with the E left, and in the standard model, we know that's a sign of the fact that they form a doublet under SU2. Now, the particles in the standard model, the right-handed particles also seem to form pairs like that. There's the upright and the down right, and the new right and E right. They seem to form analogous pairs, but in the standard model, there's no SU2 force connecting them. But in the left-right extended model, there is. So anyway, there's this famous. Okay, sorry. Let me give myself more space. So I see I'm getting close to the end here. I should. I'll just quickly wrap up. So here's the 2 + 1 splitting. Now we had hoped to find the fermions living here in the previous in the exceptional Jordan algebra, but that hope was disappointed. So now what I'm saying is that if we do the analogous analysis with H3O, just the complexified version of the previous analysis, now it is true. So now we don't quite get the standard model gauge group, but we get this extension, which, as I will explain, may be even more interesting than the standard model gauge group. It's been considered by particle physicists because it has some explanatory advantages. So, but we get this subgroup, and now the particles here do transform exactly like the standard model fermions should transform under this slight left-right symmetric extension of the standard model, if you want to get back the actual standard model at low energies. So the idea is that now the table for this model looks like, if we did the analog of our previous table, it would be SU3 times SU2 left times SU2 right times U1. And now the table would be simpler than our standard model table. So there's the left-handed quark doublet, but then there's also the right-handed quark doublet. Now we've grouped the upright and downright into a corresponding right-handed quark doublet. So the left-handed quark doublet transforms like a 3 under SU3, like a 2 under SU2 left. This is the familiar quark doublet. So it's a 2 under the familiar SU2, but it's a singlet under the new SU2, and it has U1 charge 1/6. The right-handed guy is the same, but left and right get swapped. So it's 3, 1, 2, and 1/6. Okay, so those are the quarks. And now the leptons and the Higgs are as follows. So there's the left-handed lepton doublet, and also the normal Higgs doublet, which I used to call, I guess I called it little h left, little h. I'll now call it little h left. And so it now transforms as 1. The lepton doublet and the Higgs both transform as 1, 2, 1, and minus a half. And then we group the right-handed leptons into a doublet. And we also introduce a new Higgs, which is the right-handed Higgs, the right-handed analog of the normal Higgs doublet. So this guy transforms as 1. It's just, again, we just swap left and right. So this is 1, 1, 2, minus a half. Okay, so that's the table of the leptons and scalar fields in this theory. And this theory has recently been studied by Hall and Harigaya in a series of very interesting papers, which by coincidence came out at about the same time as Todorov's papers came out. And this theory has been noted to be very interesting by them for phenomenological reasons, I mean, having nothing to do with the exceptional Jordan algebra, for the following reasons. So first of all, if you give this theory, if you demand that this theory has the sort of natural parity symmetry that you might guess, if it has a kind of parity symmetry under swapping left and right, then that turns out to solve the strong CP problem. This is, for my money, the most. So I should say, first of all, this theory. Let me, in case it wasn't clear. So you start with SU3. So this theory breaks right down to the standard model. So it works like this. So we had already seen that SU3 times SU2 times U1, which is the standard model gauge group. And so now I'll call this SU2 left. That when the Higgs left, what we used to call the Higgs, and now I'll call it the Higgs left. When the Higgs left gets a VEV, that breaks down to the unbroken part of the standard model gauge group, SU3 times U1 electromagnetism. But now here there's one previous stage where we started with SU3 times SU2 left times SU2 right times U1. And now, So at some higher scale, H right obtains a VEV, and when it does, this theory automatically reduces to this theory, and then when H left obtains a VEV, we get down to the low energy world that we observe. So this theory is perfectly compatible with the standard model. It becomes the standard model when H right obtains a VEV that is at a larger scale than what we've observed so far. And so Hall and Harigaya point out that this theory has the nice advantage that there's this so-called strong CP problem in the standard model, which is that there's an extra term which should be there in the standard model as far as the normal understanding goes, but that extra term predicts a non-vanishing electric dipole moment for the neutron, which we don't observe. And the question is, why isn't it there? The standard model seems to have allow this term, but why isn't the term there observationally? So this theory gives, the most popular explanation for that involves the axion. But for now that I've seen this solution, I must say that I think this looks to me like the most elegant solution I'm aware of that problem. And then they point out that it also fixes the gauge coupling unification in the standard model. Famously, grand unification predicts that the three gauge couplings in the standard model corresponding to the G3, G2, and G1 corresponding to the three gauge forces, that they should unify at high energies. But when you actually run the observed gauge couplings to high energies in the standard model, they don't unify. So this theory turns out to fix that problem. So it fixes gauge coupling unification. Famously low energy supersymmetry also fixes gauge coupling unification, but the LHC has not seen evidence for low energy supersymmetry. It seems likely that answer is not the correct one. So this is a different way to fix the coupling unification. And then the third point is that this theory predicts that the quartic self-coupling of the Higgs should, when you run it using the RG equations, when you run it to the UV, you should see it vanish at the scale corresponding to the vacuum expectation value of Higgs right, of the Higgs with the larger vacuum expectation value. And so that's, whereas observationally we see that the observed value of the quartic coupling of the Higgs, when we discovered the mass of the Higgs to be 126 GeV at the LHC, that implied that lambda, that let us determine the value of lambda and run it to higher energy scales. And the surprise was that the best fit value. The best fit values predict that lambda should run to 0 and should become negative at about 10 to the 11 or 10 to the 12 GeV. So in this theory, this predicts, this explains, if you want, why it runs through 0 at that high scale. It says that if that high scale is nothing but the VEV of H right, that's exactly what you should see from a low energy perspective, but that in reality, it never goes negative. The Higgs potential does not actually become unstable like it seems to in the standard model. Instead, what happens is just that the standard model is replaced by this more complete theory at high energy scales. So I'm getting to the end of my time, so maybe I should wrap it up there. So just to summarize the story so far, I think that there's an interesting connection that has been pointed out between the exceptional Jordan algebra and the standard model. That connection becomes even better, and in some sense, because it connects it brings the fermions, the standard model fermions, into the story in a way which connects with our earlier SO10 unification hint. If we replace the exceptional Jordan algebra by the complex exceptional Jordan algebra. But the price that we pay is that instead of getting the standard model gauge group on the nose, we get this left-right symmetric extension of the standard model. But the good news is that this left-right symmetric extension was already considered independently by phenomenologists because it seemed to have all of these striking, nice explanatory features about things that otherwise were observed but unexplained facts about the Standard Model. The final thing I just wanted to mention quickly is about 3 generations. One of the reasons that people have been interested in the exceptional Jordan algebra is because of its threeness, that which is not just a trivial element. And it's not a coincidence. It's related to this property called triality, which is this very special property that all of the norm division algebras, but especially exhibit this property, is related to this famous fact that the SO8 Lie algebra has 3 different 8-dimensional representations: the vector representation, the left-handed spinner, and the right-handed spinner, which all have the same dimension. And even though they're not equivalent representations, they are triality-related representations. They're very you can essentially permute the 3 representations between each other, even though they are not equivalent in the traditional sense. So that the fact that there are these 3 different representations, that's really exactly why there are 3. That's really why this is a 3x3 matrix that appears in the exceptional Jordan algebra. That's sort of that special unique property of SO8, that it has this kind of triality property which no other simple Lie algebra has, is why there is this exceptional Jordan algebra with 3x3 matrices of octonions exists, why it is still a Jordan algebra. So there's a sense in which, I just got the standard model fermions, I just got the standard model fermions by cutting up this Jordan algebra into 2 plus 1 in one way, but there's other ways I could have. There's really 2 other ways I could have cut it up. I cut it up by fixing this element and letting the other guys mix, but instead I could have cut it up by fixing this element and letting the remaining complementary part of the matrix mix, in which case I would have gotten a different embedding of the standard model fermions in this algebra, or I could have fixed this third element. And so there are these sort of 3 canonically related ways that are related by this triality symmetry, that where you can any of those ways gives a way of splitting up the algebra and seeing the standard model fermions appear, but as soon as you have one way, there are these 2 other canonically related ways that appear. It's natural to hope that this is related to the reason for the existence of 3 generations in the standard model, but anyway, there's a lot to be worked out to see if that really is right, and I've been thinking about that since this paper, but anyway, that's still work in progress, but I'm excited about it, and I guess maybe I'll stop there. Any questions?
Very nice, Latham. It's very interesting, and I did not know any of these developments. It is very fascinating indeed.
Oh, thank you.
I just wonder whether this can be casted, this Jordan algebra can be taken in the, can be used as one of the ingredients of the spectral triple formulation, Ella cones, and his program can be run through using this Jordan algebra?
Yeah, that's a very interesting question. So Shane and I had a paper back in December of 2019, sort of advocating for doing that, trying to replace the usual algebra that Kahn works with the Jordan algebra, and in particular giving a suggestion for a Jordan algebra which seemed to agree most directly with the standard model, but that was before I had figured out this thing about the exceptional Jordan algebra, and so now I'm curious about that myself. I don't I think that's a very interesting thing to look at. I haven't had a chance yet to study that myself, but yeah, I agree with you. It would be cool if one could write down the action that way and maybe get some predictions that are, well, right or wrong, I guess. And there's yeah, maybe that's all I'll say. Are there any other questions?
Any other questions from anyone else? Sumit Vishwas?
It was a bit of a blitz, I know.
Professor, there is no right-handed doublet in our present time, observable right-handed doublet in our present time. But you are saying that if we can, even in CERN, we can we can go to high energy, then we should find right-handed neutrino or right-handed doublet, right?
So it's first of all, you're absolutely right that we have not. In the quark sector, we do see the doublet. We see the we see the the upright and the downright, which would be the putative doublet. But we don't see any evidence at CERN. We don't see any evidence yet for them being related by an SU2 gauge field. And then you're also right that in the lepton sector, although there may be indirect evidence from neutrino oscillations for the right-handed neutrino, we have not yet detected a right-handed neutrino, so we don't really know that it exists. So there's sort of indirect experimental evidence, and then there's also this theoretical evidence coming from SO10. And then it's also useful cosmologically to produce the matter-antimatter asymmetry and to explain the dark matter. So there are these various indications that it exists, but we haven't yet observed it, so we don't really know. But yes, so in principle, a higher energy collider would be able to see these right-handed SU2 forces and the right-handed neutrino. Now, in practice, it seems like the energy scale, if the Hall and Hari-Kaya picture is right, the energy scale at which all of these new particles come in is so high that it's so 10 to the 12 GeV is 9 orders of magnitude higher than the energy scale that the LHC probes. So if that's really the energy scale, and there's some uncertainty in that, maybe it's as low as 10 to the 8 GeV, but still it's so much higher than the energies probed by the LHC that it is hard to imagine that a terrestrial particle collider will be able to directly observe it, although in principle a particle collider could at sufficiently high energies. It seems more likely that that experimental, predictions and confirmations of these theories would have to come by more cosmological or indirect means. For example, Hall and Hari-Kaya have pointed out a number of observational predictions of their theory, but they don't have to do directly with doing high energy colliding experiments to reach those predictions. Instead, they have to do with very precise predictions about proton decay and also about the relations. They're able to extract very precise predictions about about certain relations that the standard model parameters should be found to obey once the error bars on those parameters get sufficiently small. So stuff like that, I think, is more the way one would have to try to observe it.
You're saying that the neutrino oscillations somehow indicate the presence of right-handed neutrino, but I know that there are mass differences. Just I mean the tau neutrino and the electron neutrino, the little mass differences make them oscillate and change their gauge eigenstate to mass eigenstate, right? How they indicate the presence of right-handed neutrino?
Yeah. Yeah, so this is something that this was actually related to the question that I was answering right at the beginning of the lecture. So something which I didn't have a chance to explain very well in the lecture is that, okay, so once upon a time, let's say when the Standard Model was originally invented, neutrinos were believed to be massless. And at that time, it was assumed that the Standard Model included, that the lepton sector would have not included the new right row in our table. So instead it just included the left-handed lepton doublet, which consists of nu left and e left, and then also the right-handed neutrino, the right-handed electron, but no right-handed neutrino. Now, if you write down the renormalizable terms in the Standard Model Lagrangian using just these fields, you'll find that you can't write down a mass term for the neutrino. So the neutrino is, in some sense, predicted to be massless. So that's what they thought was the correct explanation of the observations at that time. Now, two things have happened since then. One is that we've observed neutrino oscillations, which indicate that the neutrinos have a mass. But also, people have come to understand how to work with non-renormalizable Lagrangians as include the non-renormalizable terms in the Lagrangian. And just think of it, okay, so if you include the non-renormalizable terms in the Lagrangian, well, it's no longer a complete theory on its own right, but it's still can be treated as a low energy effective theory to some larger, more complete theory. So you can get the neutrino, so which is to say that in the Standard Model Lagrangian, let's say the Standard Model Lagrangian, let's say you first wrote down the renormalizable terms, the terms with mass dimension, the terms consisting of operators with mass dimension less than or equal to 4. Well, those are the terms that dominate the low energy physics, it turns out. Those are going to be the terms that are most important at low energy, which explains why this part of the Lagrangian does such a good job of describing the observations we have made. But the leading, if you try to write down, Stephen Weinberg pointed out, if you try to go beyond the renormalizable terms and treat the Standard Model as just a low energy effective theory to some high energy, more complete renormalizable theory, well, the first term you would write down are the first terms you would add, the most important, the correction terms you would expect to be most important are the dimension 5 terms. And it turns out, Weinberg pointed out, actually there is only one dimension 5 term you can write down in the Standard Model. That's the so-called Weinberg term. And that term is, so that's the leading non-renormalizable operator you can write down in the Standard Model. And that term is built from, you contract the left-handed lepton doublet with the Higgs doublet, and then you square that. And that term turns out to have dimension 5, and so you have to divide it by some high mass scale to get the right dimensions. So then when the Higgs gets a VEV, this term acts like a mass term for the left-handed neutrino and it's a very light mass term because it's suppressed by some high mass scale lambda. So in that sense, you can explain the observed neutrino masses without adding a right-handed neutrino. If you instead say, it's the the neutrino masses are due to the first non-renormalizable correction to the standard model. But in a sense, that just puts off the question, because once you start adding the non-renormalizable terms, those terms have come from integrating out some higher energy physics from some more complete theory that was renormalizable. And so the question is, what is that more complete physics? So the simplest renormalizable extension of the standard model that gives neutrino masses is to, instead of adding this term, to just write the effective theory for the low energy effective theory, the simplest extension, which is still renormalizable, the simplest complete theory, which includes neutrino masses, is where you add the right-handed neutrino, and then you can write down mass terms that are renormalizable, that are just built from the Higgs and the right-handed neutrino and the left-handed neutrino. So in that sense, that's the sense in which neutrino masses and oscillations are evidence. So neutrino oscillations, like you say, are evidence for neutrino mass, because they show that there's a difference between the mass eigenstates and the flavor eigenstates, which would only be possible if the mass eigenstates had non-zero mass. And then the question is, what's causing the neutrino mass? And one answer would be the first one I mentioned here, that it's just the non-renormalizable corrections to the standard model Lagrangian without adding the right-handed neutrino. But that begs the question of what is the higher energy physics you integrated out? And the simplest extension of the standard model, which answers that question, is that it is where you add a right-handed neutrino. So yeah, is that clear? So in other words, it's true that there is. I just want to emphasize that we don't know. There's not sort of certain experimental evidence that the right-handed neutrino exists, but in this sense, there is this and other indirect evidence that it exists. So there's enough evidence that it exists that I would say it's probably more than 50% likely that it exists, but we don't really know. All the other particles in the standard model, we've actually observed them. We know they're there. This one does not yet have that status.
So left-right symmetric model can give the answer, embed the neutrino mass, right?
The left-right symmetric model, yeah, has to have the right-handed neutrino, and it does explain the neutrino mass, yeah.
Okay. Thank you, Professor.
Sure. Thanks for the questions.
Hello. I have a
Yes.
question that what is the major changes would you expected if one try to extend the existing standard model at Planck scale or just before Planck scale?
That's a good question. You know, if you well, you know, if you try to go above the Planck scale, I tend to not really know what to expect up there. I personally feel like it's such a big extrapolation from what we currently know. I don't feel very it's an understatement to say I don't feel confident about what I expect there. Meanwhile, below the Planck scale, where you kind of expect, which is the regime where you kind of expect, and at times well after the Planck time, if you kind of, which is would be the times in the early universe, you know, when the energy scale had already dropped well below the Planck scale. That's kind of the regime where you do expect the kind of
Is a part of the algebra will be changed at the if one try to extrapolate the standard model to Planck scale?
Well, we don't know. It's possible. You know, definitely the usual approach where you treat gravity semi-classically, you treat the standard model fully quantum mechanically, but the gravitational part of the action can be well approximated by, a classical space-time manifold, possibly with small quantum fluctuations in the graviton field. That will break down, or presumably will break down at the Planck scale. Now, I must say that another thing, a sort of independent topic that I'm interested in has to do with making theories that are locally conformally invariant, where you gauge conformal invariance, and there, part of the appeal of such a theory is that if you had a nice extension of the standard model that had a conformal gauge symmetry, then it would, maybe it would make the, since all scales would become equally good in such a theory, there might be some sense in which the Planck scale would become a less scary transition point, and maybe you could have a theory that was valid at all energy scales without major changes. But we've not yet successfully written down such a theory, so we've been thinking about it, but it's not clear whether such a theory is possible to write down. So that would be kind of the minimal possibility where not much changed. I'm sort of interested in trying to find, the minimal extension of the standard model that explains everything we see and kind of everything we see both in laboratory and experiments, and kind of only do something more ambitious when I'm absolutely forced by experiment. I just kind of like that approach to see what's the minimum one can get by with. And so in principle, that one could imagine something like that as a very minimal possibility, that just basically the current standard model, but coupled in a slightly different way to gravity to make it conformally invariant, by adding a Weyl gauge field. Weyl had an idea back in the early days of general relativity about how to make a theory conformally invariant, which I think is very interesting and I've been thinking about. But so that would involve sort of one extra gauge field for Weyl invariance, but then would make a theory in principle that might be valid at all scales, without modifications necessary. But really, I don't know. It's also possible that something more like what you're suggesting happens, and that the algebra of the space-time symmetry algebra has to get mixed up with the internal symmetry algebra.
Oh, you said diffeomorphism symmetry, internal symmetry can be mixed up.
In principle, maybe there's something like that happens. Famously, that's hard to do. There's this Coleman-Weinberg theorem Coleman-Mandula theorem that makes it hard to, says it's hard to mix the internal and space-time symmetries without screwing up the S matrix of the theory, but in an ordinary quantum field theory. But yeah, who knows? No-go theorems are made to be broken. It's possible. It's definitely possible that they get mixed up at those scales. Certainly a more, the natural expectation, given what previous examples of unification, yeah. When you unify two forces, you end up mixing their symmetries together, and so you would naturally, in that sense, expect something similar to happen when you unified the three forces with gravity. But how exactly that should work is, I personally don't know. I guess the string theorists have one answer, but it's a little bit skimpy on the specificity.
Okay, thanks for the clarifications.
Sure. Yeah. So also, I feel like I didn't clarify very much. So sorry, I couldn't be more clarifying there. But I don't know the answer myself.
No, it's okay.
Hi, Professor.
Yes.
You mentioned that octonions are finite in number. So why is that the case?
Do you mean that I think I said two different things. One is that they form an 8-dimensional algebra. Is that the finite number you're talking about, or that there's only these 4 number systems?
No, that's finite dimensional one. Oh, 8-dimensional.
Oh, why are they 8-dimensional?
Yes.
Well, so there is this. Let's see. So I said that there were only 4 norm division algebras, and their dimensions are the powers of 2. They're 1, 2, 4, and 8, and that's not a coincidence. The reason for that is that the way you prove that there's only these 4 norm division algebras is that you prove that if you have a norm division algebra a norm division algebra means an algebra with all of the usual properties of a number system. You can multiply, divide, add, subtract, and the numbers have a size, which if you take the product of 2 numbers, the size of the product is the product of the sizes. And you can prove that such an algebra, if you have such an algebra, there's a way to take half of that algebra, and when you take half of it, that will still be a norm division algebra. So it follows from that the fact that if you have a norm division algebra, then a certain half of it will also be a norm division algebra, ends up implying that they all have to be powers of 2 in dimension. So that's why, in a sense, that's why they all end up being powers of 2 here. And then the reason that you don't get any higher powers of 2, the reason that the last one has dimension 8, is that you find that if you follow that line of argument in the opposite direction, each of these gets they kind of lose good properties as you follow them up the chain here. And so when you get to the complex numbers, when you started with the real numbers, when you get to the complex numbers, they had a new property which the reals didn't have, which was complex conjugation. When you get to the quaternions, now in addition to conjugation, non-trivial conjugation, they have another new property, which is that they're non-commutative, that Q1 times Q2 is not equal to Q2 times Q1. When you go further to the octonions, you get yet another new property, which is that in addition to having a non-trivial conjugation and to being non-commutative, they're also non-associative, so it's like x1 times x2, x3. The answer depends on where you put the parentheses now. And then if you tried to go further, they lose the norm division algebra property. It's no longer the case that you can form 16-dimensional algebras, but they no longer have these properties that you can always divide, that any number has a unique multiplicative inverse.
Okay. Thanks.
Okay, sure. Any other questions, or is that it? If that's it, then let me just say.
I think so.
Let me say thanks.
So I think
everybody.
that's all. Yeah, we also thank you, Latham, for agreeing to give the talks here.
Oh,
and
yeah,
it was a big, it was really wonderful. set up
Oh,
3
it's a lot of fun
lectures.
for me.
Means all of us, I think many of the students have enjoyed very thoroughly. And some of them, in fact, requested, as I told you yesterday, that they wanted you to give one more talk, but I think it will be too much burden on you, and I don't want to go for that. But in future, maybe if some of them want to pursue these things, they may contact you individually if they want.
Sure. Sounds
So,
good. Yeah, I think this makes a nice. I have a feeling this is probably for a taster level introduction to these things. This is probably a reasonable stopping point. As I mentioned, if you were going to do more, if you were interested in more, I do recommend. My lecture videos from last year do cover these topics, but in essentially these topics, but in more systematic detail over. It's more like 20 lectures, so it's kind of a jump. But anyway, if you're interested in more, and then also, as I mentioned earlier, but just to mention it again, I will be sharing my lecture videos this year, which will include this most recent paper, which the previous year's lecture didn't, on YouTube in a few months. So anyone who's interested in that, please, you can feel free to get in contact with me by email, and I'd be happy to point you to those lectures when they appear.
thank you. Atri, you want to say something?
Yeah, I just wanted to thank him. Actually, this one exactly I wanted to tell that he has already informed us that anyone interested can go and attend the lectures, which he is supposed to give this semester. And maybe the previous semester lectures also they're available, he told. So students are always, I think they can, depending upon their interest, they can go and then go through those lectures or attend the classes when he's taking. I don't know whether they'll be open, but he told in the YouTube. So, it's open. Live, it may not be open, but they can always get back to him through email. I think so, Professor Boyle.
Yes. And my email address is LBOYLE. That's my first. I'll write it down here.
Yeah, so it was really nice to have you here, and really, it was almost blackboard talk. I understand that it's difficult, but then also we have a habit of attending blackboard talks, and somehow I enjoy that more. But it was almost like a blackboard talk, and I really enjoyed it. And then I feel also the students also, because somehow I feel that it's my personal thing that if, I feel that if you are showing up all points, somehow there is a not that detailed.
I find it easier to.
It's always, and it's so nice that you could spare so much of time taking pain to do all those things. And thank you so much. You were, otherwise you have so many commitments, and then also you agreed to the invitation sent for this. And with this, this Silver Jubilee celebration also becomes a more meaningful one. So thank you, Professor Boyle, so much. And if possible, we would like to schedule tomorrow's, ending ceremony.
Yes.
Not ceremony that way, but I will let you know if possible. Kindly be there at least for a few minutes, if possible.
Sure.
I know you have lots of commitments, so not that way. But
no, that's
for that,
okay.
I think it will be better to reschedule it at 6 o'clock at least. Otherwise, if it is scheduled at 4 o'clock.
Yeah, that is what I will discuss with you and write back for the experts and also the participants. So we will try to see that everyone can join. The time schedule should be such that. So we will try to do it.
Okay.
And another thing, Latham, is this: all these pages that you have written on. Is it possible to send it? Somehow, even these things are quite useful, I think.
Probably so. I'll try to figure out how to do that, and I'll send them.
Okay,
sure, I'll send them to you.
Just send it to Atri. That will be very good.
Okay, I'm having a little trouble hearing, but so that sounds good. I'll send those, and thanks again to Biswajit and Atri for the invitation. It was really fun, and thank you everyone who's if anyone's left for listening. I appreciate it very much.
Thank you so much, sir.
Okay, very good. Bye.
Take care.
Thank you so much.
We are almost at the end. We have one more lecture of
Yeah.
Indirajan tomorrow left. So I hope.
At what time is it scheduled?
It is
At what time?
1:30.
It is at
2 o'clock.
it is at 2 o'clock. Okay.
Yeah.
So
Possibly
let us know
we'll
at what
have
time
this-
this.
Yeah, possibly we'll have this concluding session around 6. I think that will be better. Everyone can be there.
Yeah.
Yeah, and then
6 or
even later, late at 6:37.
yeah.
And then we don't have anyone from Far East, so it should not be a problem actually. And then
Yeah.
one more thing, this exam matter. Will we do it day after tomorrow?
Yeah. Do it day after tomorrow. Have you requested Professor Boyle to send a couple of questions?
Yeah, I will again write to all experts separately. Just like Bharveli, I told him.
Oh, you told him verbally. Okay,
Yes.
that's good. So maybe you can just send him an email so that they can send the questions by tomorrow itself.
Yeah.
I'll
So,
send
right now,
mine by tomorrow.
also the Rashtrapati is already sent. I'll share with you.
No, you need not share with me.
You have to write an exam to get a certificate. So we'll arrange an exam for you day after tomorrow.
Maybe send a notice to all the students who are willing to have this certificate. They need to write this exam. Just
Yeah. That already once I have written, once we fix up the time and everything, then I will let them know again.
okay then.
Okay then.